Hello, everyone. So I'm Jinkun from NYU. So today I'm happy to share our recent work on straggler understanding in large model training using what-if analysis. So this is a joint work with folks at ByteDance and Zhejiang University. So we were motivated by many observations of stragglers at ByteDance. But in many cases, what caused the stragglers and their severity remained unknown. Although there have been many reports on stragglers, but they do not provide satisfactory answers because they are mostly like scattered case studies, and they are kind of they only cover limited number of settings. So in this work, we aim to study stragglers more comprehensively, and we do so using a 5 months trace dataset collected from ByteDance cluster. So in this talk, I will first talk about how we analyze stragglers using what-if analysis, and then the analysis result and how we use this analysis algorithm in production. So what I mean by a straggler is a worker that is slower than others at synchronization time. For example, here shows a synchronous SGD algorithm implemented with a data parallelism, where every process represents one worker, and at the end of every chaining step, all workers will synchronize with each other to collect the full gradient before moving on to the next iteration. And as you can see, for example, in the first step, the second process is a straggler that prevents others from making progress. But why are stragglers also relevant to LLM training? Because this kind of training uses several parallelism strategies together. Here shows an example of data and pipeline parallelism, where all GPUs are arranged in this 2D mesh, and every GPU gets assigned one DP and PP rank. Along the PP dimension, the model is partitioned into multiple parts, and one PP rank gets assigned one part. And along the DP dimension, the same partitioning is replicated to all the DP ranks. And to conduct the training, every GPU receives the data computed from the previous PP rank and computes all the layers locally assigned to it and sends the result to the next PP rank. So we will have peer-to-peer communications between neighboring PP ranks. And after you finish the backward propagation, you will synchronize the gradients with every other GPU in the same PP rank. So you will have this collective synchronization along all these GPUs. And both synchronizations both communications will have synchronizations. So that's why stragglers can happen. So our traces to study this problem, we collect this set of traces that it has 3,079 pre-training jobs collected from our homogeneous clusters dedicated for LLM training. And the job sizes range from 128 to more than 5,000 GPUs. And the parallelism strategies include data pipeline, tensor, context, parallel, and their combination. And each job trace has around 10% of the training step sampled. And each sampled step was traced by our in-house provider called ND Timeline. And the record of the trace contains timestamps of coarse-grained operations at every worker. And this may be clear with an example in this timeline view. So here shows a job using two-stage pipeline parallelism and with 2 macro batches. The trace will record the start and end times of the following operations represented in the boxes here. And they are arranged in different lines where every line represents one CUDA stream. In the computation stream, you will have operations for forward and backward propagations. And they are recorded in this granularity of entire pipeline stage instead of individual layers. And in the communication streams, you will have forward send receive and backward send receive kernels. operations. Sorry. So these are recorded in this nickel kernel granularity, and they represent a peer-to-peer communications between the two neighboring PP ranks. If you use data parallelism in a 0-1 style, which is a common variant of DP, you will have one more stream containing the all-getter and reduce-getter kernels for data parallelism in every worker. So given such a trace, how do we know if a job is suffering from stragglers? So we use counterfactual reasoning. Think about this. If there is no straggler in this job, what will the trace look like? We argue that you will see the following happen. All forward compute operations should take the same time, and same for backward compute operation and all other communication operations. Because in a straggler-free case, all workers should progress in the same speed and they finish all of their assigned tasks at the same time. In such a case, the job should have the lowest job completion time, and we denote it by T ideal. And we define the straggler-caused job slowdown as T over T ideal, where T refers to the actual job runtime. And we calculate this T ideal using what-if simulation, which consists of two steps. One, adjusting every operation's duration to an ideal value, which is determined by taking the average for computation operations and median for communication operations. So let's take a look at this example. So you have a struggling trace where rank 1 is assigned more workload than rank 0. So the first step is to adjust all the operations to ideal one. In this case, we take the average. So you see the operations of 1.5 for F here. And the second step is to simulate the job run using the adjusted durations. And this is done with a topological sort based on manually encoded dependency graph. In this case, you will simulate these adjusted operations so that they obey the data dependencies. In this case, the backward should happen after the forward. So now let's look at some analysis results and the findings. So in our analysis, we answered the following questions about stragglers. So first is the prevalence and impact of stragglers, and then the symptoms of stragglers, and the common root causes and their relative severity. Let's look at the prevalence first. We plot the slowdown of all the jobs in this CDF graph, where slowdown is shown in x-axis, represented in percentage and in log scale. If we define jobs with slowdown larger than 10% as struggling, we see about 42.5% of jobs struggle, which means strugglers are quite prevalent in our cluster. And on average, the strugglers have caused a 1.15 slowdown, but at the tail, they could cause a much more severe slowdown, which is 2x. Therefore, stragglers are an important problem in our cluster. Now let's look at what caused these stragglers. We identify the major causes by sampling large jobs with high slowdown and then conducting manual inspections and further analysis. So the first root cause we studied is worker problems. It refers to the case where the job is struggled by a few slow workers. And this is a superset of hardware problems because we expect most machines are healthy. To quantify the severity, one important metric is how many jobs are affected. And the main idea here to compute this number is that we think fixing a few workers should recover most performance. So we identify this set of workers with the slowest 3% workers, W, and we try to estimate the runtime of the job had this set of workers been fixed. Of course, we cannot really fix the worker and rerun a job, which is too expensive. Instead, we simulate this quantity with a similar what-if simulation you seen earlier. But instead of adjusting all operations, we now only adjust loads on W. And to know what is this set of slowest 3% workers, we use a new metric called worker slowdown, which measures the slowness of every worker. Now we have this TW ideal. We can know how much performance can be recovered by fixing W. And then we compare it with the total performance to recover and define their ratio as MW. And in this case, MW should be large. So we show the MW of all the workers in this CDF graph. And we choose a relatively high threshold, 50%. And surprisingly, we find that most jobs are actually below this threshold, meaning that worker problems are not a common cause in our cluster. But we also check those jobs with high MW, and we find that they actually have higher slowdown, which is on average 3.04, much larger than the average slowdown 1.28 of the entire pool of the struggling jobs. So these findings imply that traditional health metrics are important, but still insufficient to help avoid most strugglers. So the common root causes we found are PP stage partitioning imbalance due to lost layers. This has affected 39.3% of the jobs, and also sequenceless imbalance and Python's garbage collection. We also found some other uncommon but interesting causes, and please check our paper for detail. And now I would like to talk about how we use our analysis in production to detect stragglers. So part of this analysis has been deployed at ByteDance into a monitoring service called SMO. It has provided two benefits for us. First is that it can continuously monitor all running jobs in real time for straggler detection. So this is because we, in our cluster, have a default on profiler that traces every running job and upload the trace periodically. For every newly uploaded trace, our SMO system will automatically analyze the trace and report various straggler-related metrics like the slowdown estimation. This allows us to configure various alert metrics based on a report. For example, the operation team at ByteDance has configured to alert on large slowdowns and patterns indicating worker problems. And the second benefit is that it facilitates manual troubleshooting when we need to diagnose a specific struggling job. This is enabled with a heat map representation where each cell represents a worker and the color represents the slowdown of the worker. And it can help us locate the slow workers very easily by looking at what cells are highlighted. So here it shows the stage partitioning imbalance, which is caused by a large loss layer assigned to the last PP stage. And the last row in this heat map represents the last PP stage, and that's why they are highlighted in this case. And it can also help us identify the root causes by looking at a pattern of the heat map. For worker problems, because they should only affect a few number of workers, so you only see a few cells highlighted. For sequenceless imbalance, which is a problem that uniformly affects all workers, should highlight everyone. So in summary, we present a comprehensive and quantitative study of stragglers on a production trace dataset, which studied straggler impact, symptoms, and root causes. And this analysis algorithm has also led us to develop and deploy this monitoring system ESMO, which helps us monitor and diagnose stragglers in production. And with that, thank you for your attention.